And as a second disclaimer, also, many of you have heard about quantum computing, know that one of the big goals in the last 30 years in quantum computing is to speed up algorithms, to make intractable algorithms tractable. Also, this question of like, can quantum computers speed up machine learning and do these crazy things won't be answered here, because you will see quantum machine learning is a very diverse field. It is more asking questions at the moment than answering them. It's starting to like develop techniques at the moment, and so it is a lot broader than you probably expect. So let's look into it. Please ask questions anytime. So since this is a long lecture, let me just see. Oh yeah, there we go. Cool. So first of all, let me give you a bit of a background story, because as I said, like not everyone will know what's going on here. Quantum computing is quite old by now. It has started kind of in the 80s or 90s, where people thought, how can we use quantum theory to build computers or to process information? And they found a couple of very interesting things that these computers would be able to do. But however, there is something that happened in recent years, and that is what splits basically quantum computing into good old quantum computing. So there's research that people have done theoretically about these machines for 30 years, and what we would call near-term quantum computing. And that thing that happened is that actually quantum computers started to be available. They started to be like programmable. And those types of quantum computers that we have today, and we have since a couple of years, they're not really the machines that people envisioned when they invented what some of you might know as SCHULD's algorithm or Grover's algorithm. So where we know all the complexity proofs of, where we understand complexity classes more or less. But these near-term quantum devices, they are small. Think of them as FPGAs or little ASICs, or like little devices that you can program, like maybe a little chip or whatever the platform, physical platform is that implements the quantum computer, and there are many. So they're noisy. So basically you kind of read out a result and it will be off by a large percentage, and the error propagates very badly. So we can only run extremely short computations that are like really tailor-made for the device. And think of programming a quantum computer really being something like, I don't know, back in the 40s or 50s, like programming real computers. You really have to know almost which of the systems you address and which one is working well and how to swap them in some else. So it's quite exciting, but it's also very challenging. And there are a lot of challenges now that you know, are also present in quantum machine learning because of that. So quantum machine learning also like splits almost into these broad categories: the old school quantum machine learning, and then kind of quantum machine learning with near-term devices. I mostly focus on the near-term stuff, and you know, so just as a notion, like, so quantum computing was always something that was only for like research scientists who had spent years of physics education and stuff. Also, since a couple of years, this is not true anymore. So you can, for example, here in this IBM interface, which is the most popular, I guess, but there are lots of very, very interesting different like quantum computing interfaces. So here you can, for example, program and run a quantum computer in the cloud. And most companies and startups actually offer services like this. Since this like near-term split, like we have attention from lots of the industry, and this is interesting maybe to refer back to, so in machine learning, you guys know this very well. So with the advent of deep learning, this happened. Like all of a sudden, a science became actually a mixture of industry and science. And at the moment, what I see, like it's splitting away again. In quantum computing, we're almost like just at the beginning of this process where all of a sudden there's money involved. And so now all these companies are investing into quantum computing, and what do they need? They need an application, and they need an application that kind of they can sell to their investors now. So they need an application that doesn't care at all if your results are noisy. So you can't really have, for example, you can't require like an exact result, for example, find one string or crack a code or something like that. It needs to gain money, and also like not to underestimate, like we need young people interested in the field, and we need a lot of talent at the moment. So it's actually quite scarce. Like all people are bought up very, very quickly once they graduate in their PhDs. So what can we do? And this is probably one of the reasons why machine learning or quantum machine learning has gained so much attraction in the last years. However, there's actually a really interesting basis to trying to combine quantum computation and machine learning. And so machine learning is based on lots of hardware, and it's also quite hardware driven. So whatever the hardware like computers can do, limit basically what machine learning can do. And as all of you know, like a lot of the success in machine learning was based on like hardware getting better and better, like GPUs being available. So it's really interesting what happens if we put two new devices in the mix. So I would say like that these new near-term quantum devices would sit somewhere here as like little accelerators or little chips that can do like very small things. But then also we should start like continue thinking about these big quantum computers that people will produce in the future. That's basically the end goal of this whole process. So what happens to AI and machine learning in that way? And I want to give you an executive summary of basically the whole overview of the field of quantum machine learning in this slide. And it will be also the overview of the entire talk. So after this, you can basically switch off, or if something interests you, you can stay on. And I think a very good way is to kind of define machine intelligence or machine learning as a mixture of these three very famous pillars. The one is like data, and data often comes from distributions. So there's a lot of probability theory in this. There's a lot of like statistics and statistical theory in this. So obviously like deep learning frameworks have like big data. So like kind of the data distributions change in some ways. Then you've got algorithms and hardware. So that's basically the computing side, like the stuff that runs your machine learning models. And then in the end, there are the models themselves, so your neural networks or whatever. And obviously in deep learning, people start now to recover. So why do I split this up like that? In deep learning, they start to uncover that basically all three pillars really like put together form like the foundation of if a machine learning framework is good or not. Okay, cool. Now I want to put quantum in the mix. And quantum machine learning or quantum computing researchers have really attacked all three of these pillars. And just to give you an idea of how diverse this could be. So for example, in the data and distribution side, this was actually something people have already done 20 years ago or like a long time ago. You can go and say, so as we will learn just now, quantum computing is a probabilistic process. It's a probabilistic theory. A quantum computer is in some sense just a sampler. So you have a slightly different like probability theory underlying, quantum mechanics. What happens now if your distributions follow this like quantum theory, or if you can act on distributions, or if you can sample in a way that doesn't follow classical probability theory, but quantum probability theory? So people have checked out what happens, for example, to statistical learning theory if I replace my data with something like that one could call quantum data. On the second side, and so this happened like a long time ago already. The second pillar, I would say, like algorithm and hardware, is very much similar to the stream of quantum machine learning that I would call good old quantum machine learning. So where people like have this mentality of like what quantum computing was traditionally. And here the idea is I take a machine learning model, I leave everything as it is, so I don't like change the model or something. The only thing I want to do, I want to change the algorithm and run it on different hardware so that I speed it up. So basically in the big machine learning pipeline, what you would do is one day they envision that, for example, you have your TensorFlow pipeline and somewhere where you optimize or where you execute your model or whatever, the subroutine gets executed on a quantum computer. And the question is, can the quantum computer do this a lot faster? And by this enable things that maybe people in machine learning haven't tried or haven't thought about yet. This is a highly theoretical field, to some extent also quite controversial. I hope I get to this tomorrow a little bit. And then here's my favorite playground, and that's the models, because and this was almost like something that happened, after the first couple of years of quantum machine learning being a thing and like conferences being held and papers being published, that people started thinking, let's do it the other way around. Let's not take the machine learning algorithms from classical machine learning. Let's not take a neural network and try to make it faster, but let's actually see if our quantum computers can actually give rise to a completely different class of models. And the biggest idea, and this is what a lot of my research is in and what I want to talk about a lot today, is the idea of using a quantum computation as a model, because you can encode data into a physical state of a system. You can measure that system and interpret the measurement as a prediction or as a sample from a generated model. And then this whole process could just replace a neural network. And we will see that you can train these models nicely due to a couple of very interesting tricks. And we will see what these models actually resemble. So they resemble, in some sense, neural networks that act in very high dimensional spaces and that have difficulties in implementing nonlinearities. And on the other hand, very much they also resemble like support vector machines and kernel methods, because they act in these like feature spaces in some sense. So this was the whole kind of outline. And what we will do here, we will go actually backwards. So I want to talk about models today. And if I even don't get further than that. I think those other two topics, they're kind of like a bit smaller at the moment in the community. You could say like the discussion is a bit older. So I want to start with the models with the latest stuff, and then I will also comment on like the more theoretical and the more like established ideas and parts. Last little comment, maybe more and more quantum machine learning is known as I interpret it here now, which is doing machine learning on a quantum computer or with a quantum computer. There are lots of other intersections. For example, so this will be like kind of here, you have classical data, you have a quantum computer, and you solve a classical machine learning problem. But you could also think of, so quantum machine learning describing other intersections. So for example, if you have kind of data from a quantum experiment and you have classical machine learning, there's a lot happening at the moment. I mean, science and physics in particular is swamped by young graduate students who want to do machine learning on something, and often like the older profs don't even know what that is or how this works. And so there's a lot of, we're taking a lot of very naive steps into that direction, and hopefully soon something new will come out of there as well that might actually feed back into machine learning and do a bit more like, let's say like science aware, model aware, maybe more hand modeled feature learning than in, for example, industrial applications. So I think this is a very interesting field. And there are also the other two fields. I won't go into this at the moment. Cool. If there are any questions, like always just come in. Otherwise, we've got a very tough agenda. So I assume that most of you know linear algebra. That's, I think, the basics that you need to understand quantum computing. Obviously, I can't talk about quantum machine learning without giving you a basic introduction, but don't worry, I won't talk about physics. I won't talk about photons or anything like that. I want to do two things. I want to first give you a little intro, a couple of slides that motivate why we talk about quantum computations as linear transformations of very high dimensional vectors. So why is quantum computing actually just linear algebra in a very high dimensional space? And then I want to like kind of reset and do the same thing again and start giving you like basically a picture of how quantum computing works, and that I will use in the other sections. And then I will go through these three pillars, so to speak. I hope though that at the end of this section here, you will already be almost able to see what I will say in the next section, because the structure of how quantum computing looks mathematically is so, suggestive of what machine learning it could do. Okay, cool. Let's go. So if you ask me to summarize the rules of quantum mechanics in general, that would be probably it. I won't go through this. So we've got these funky symbols you see a lot. I won't use them at all, except from, somewhere like as pictures probably, because these are just like basically symbols for vectors that live in Hilbert spaces. And I find it very hard to actually introduce them and then start calculating with them, and no one knows what's happening. But whenever you see one of those, these should just be like symbols of vectors. But you can do the entire thing or the entire linear algebra also as matrix vector notation. Even like in the 30s, like Heisenberg himself has written down the entire Dirac formalism in basically matrix vector notation. I think this is a lot easier to understand for people. Okay, cool. Let's get the setting clear. What does quantum theory in general describe? And quantum computing is no different. The setting is always that you have a random variable, which is kind of in physics your measurement, and you take observations, so you can take different values. And I'll stick for now with like discrete and finite values here. And then what quantum theory describes is nothing else than the probabilities of these observations to occur. So quantum theory predicts like expectations or probability distributions over measurement results. And that's all that quantum theory does. So it's a probabilistic theory in its basis. This becomes important in quantum computing because people always say quantum computing is highly parallel, but what they actually mean, it's probabilistic. It kind of like goes through paths of possible outcomes in some sense. So, and now you can define the expectation value of a random variable that you all know in machine learning is nothing else than here in this setting, which is basically just the measurement result, which is in our case, we always think this is a numerical value times its probability and then the sum over it. So it's basically the average value. So now we need two mathematical steps to get to vectors and matrices, and I can't really like explain like why this is needed. Just think of it as people figured out that this describes the experiments and nature in a very nice way. The first one is this: replace your, like, let's put these probabilities here in a vector. So I will always talk, when I talk about vectors, I usually talk about probability distributions that are discrete and that are like where the probabilities are entries of vectors. So the only thing we do here, we actually take the square of these probabilities and write it into a vector. And now we call it Q. And we also like change the measurement itself. We put those measurement outcomes on the diagonal of a matrix. And now the expectation value can be computed just in a slightly different mathematical form. So we just make things a bit more complicated. And this form here is a quadratic form, so-called quadratic form. So you just multiply, sandwich the measurement operator in the middle of two vectors. And these vectors here will be your probabilities or quasi-probabilities or something. Same result though. So far everything is classical. So you could do classical probability theory in this way. But now we go quantum. And the difference to here is that you actually replace Q by a vector that has the same dimension, the same size, because your measurement outcomes kind of don't change what you can observe. But now the numbers that you describe probabilities with are now complex numbers. And this is important because they're not only complex, but they can also be negative. Like, so we don't constrain ourselves to like probabilities which are like positive real numbers. And there is a certain condition that you need to fulfill. First of all, how do you interpret now, how to get your probability out of this vector? So it's not really a probability distribution anymore, it's these complex numbers. If you take the absolute square value of every entry, you get the probability for the event that is connected or that's kind of associated with this dimension to happen. So for example, I'll give you an example just now. And then the measurement matrix, before it was a diagonal matrix. So for us, diagonal always means classical, non-diagonal, if they have off-diagonal elements, something quantum happens in quantum theory. So what you do with this measurement observable, it also becomes complex and it gets a structure that's Hermitian. Oh, I actually can see the question, this is perfect. Can you give some intuition about complex number probability values? If an intuition means why is that the case, there's absolutely no one really knows. You can apparently formulate quantum theory. So if you dig very deep into papers, you can formulate quantum theory also without complex numbers. It's a bit more like in engineering, in wave mechanics. Complex numbers are very beautiful to express all of those things. And I think this analogy is not maybe too wrong because you might have heard that quantum theory is very much based on observations that a particle and a wave, there's like ways to describe a physical system as a particle or a wave. And the wave part is really elegant if you use complex numbers. So this might be it. In my mind, what I always just think of it, it's the best description that we have or the most elegant description that we have of this whole stuff. But let me see if I can put more.
Maria, may I interrupt you, please?
Yes.
We got one more question
please.
from Slido. So the question is, you mentioned quantum data. Could you explain what is it? Is it just a result of experiments in physics, or it could be something else?
Yes, excellent question. That was actually, I gave a talk a couple of days ago. It was the same question I got. It's a very sloppy way and completely undefined. You will find researchers use this term for very different things. And me too, actually. Wait, sorry, am I back?
Yeah, we can see you and hear you as well.
Zoom kind of kicked me out there. I don't know what happened. Okay, let's hope it doesn't happen again. Cool. Oh, and actually you asked me to put this one here on as well. Sorry. Yes, so quantum data is used for data from a quantum experiment. So you do measurements and you get results out that are just numbers and you store them in a classical computer. It's classical data, but it's data produced by a quantum experiment. And other people use quantum data, to mean actually a quantum state. So basically a quantum system itself. So for example, a photon can carry information. And so the photon carries quantum data in some sense, and both uses you will find. Yeah, good question.
Thank you.
Cool, thanks. Let me go back. So we had, we turn our probability distribution into a vector of complex numbers, and we turn our matrix into a matrix of complex numbers. That's Hermitian. Why is it Hermitian? Here you see the eigenvalues of the matrix are the measurement results, and we still want this to be the case. And Hermitian matrix have actually the property that the eigenvalues are real. if that wasn't the case, it's a bit strange model, you know, like if you have complex eigenvalues or complex measurement outcomes, what does that even mean? So that's the whole apparatus. And you can do the same game here. If you like sandwich your measurement operator from left and right, you know, what you get is that from the right and from the left, you get the complex conjugated and the original value. So you get these probabilities out of here so that you get actually exactly the same expectation values again. So whenever I talk about a quantum state, what I mean is this weird probability distribution or this weird, I call it quasi-probability distribution. It's probably not mathematically correct, but it's basically the bookkeeping vector that tells us about probabilities of measurement results. And how does it tell us about it? You take the absolute square value and you get the probability of a certain event to happen. And the last little bit that we need, and this is why, you know, we have now the vectors. Why do we talk about high dimensional vectors that describe quantum systems? That's those probability vectors, those quantum states. Why matrices? So when you manipulate a system, so in physics, you always have time somehow. You change your system. If you go to the classical probability distribution, what does it mean to like manipulate your system? You might know this from hidden Markov models or Markov chains. So how you mathematically describe it, you describe it by a matrix, a stochastic matrix multiplied with this distribution, then you get another distribution. And why stochastic? Because you need the distribution to stay normalized. It has to still add up to 1, otherwise it's not a probability. Quantum physics, kind of same thing happens, but now here, because we have the absolute square values have to sum up to 1, our matrix doesn't have to be stochastic, but it has to be unitary. That's just a property of the matrix, basically, that keeps the vector nice and normalized. So now what I want you to understand from this is we describe quantum systems by unitary, which are just linear, certain type of linear transformations on high dimensional vectors that describe these probability distributions. Okay. That's kind of the block. And now if you didn't understand anything, you get another chance, because now I'm getting into quantum computing and I will do kind of use this fact that you multiply and just develop a couple of pictures, and those pictures will guide us in the rest of the lecture. Okay, let me try to describe what's going on here. On the right here is our probability vector. So this block here, this rectangular, is for me always this quantum state, and the entries are those complex numbers, and if you take the absolute value squared, you get the probability of events. In quantum computing, not in all quantum computing, but most of it, we're talking about a computer that, like a classical computer, consists of n bits. You call them just qubits because they carry quantum information, not classical information. So now, what does this probability distribution actually describe, or what system, or what measurement results? It describes the measurement results, loosely speaking at least, of observing those qubits either in state 0 or 1. So basically, it's a probability distribution over all binary strings that could happen. So by convention, the first entry is always, what's the probability that all of the qubits are in state 0? The second one is, what's the probability that the last one is in state 1 and the rest is in 0, or whichever like ordering you have then there. And now, if I write the qubit system down like here, everything is in 0. I guess you should be now able to understand why the first entry is a 1 and the rest is 0, because what does this mean? This means the probability of observing the 000 state is 1 and the rest is completely unlikely. So this like idea of so this is basically a Dirac distribution, discrete Dirac probability distribution. You could think of it like that. If you're very clever, you might also wonder, why is this a 1 plus OI? I could write anything here. I could write minus I or minus 1. All of those absolute squared values equal, 1. So it's well defined. So basically, this is not unique. Lots of quantum state can map to the same probability distribution. And what you have up here is something called, physicists often use a Bloch sphere picture. It's called the Bloch sphere. If this is a normalized vector, in some sense, you can represent it like a vector, like a point on a sphere. So basically our initial state, so obviously this would be the representation of a single qubit system. Why? Because in 3D, I can like represent like 3 variables, and a single qubit system has 2 to the 1, so 2 entries here. And all entries are complex numbers, so you've got 4 unknowns. But since it's normalized, you only have 3 because 1 is tied. So this is why I can represent a single qubit in 3D. It's not so super important, just like I find some of this nice to illustrate things. I'm not sure. So I always have like kind of the slides are always followed by code because quantum machine learning has kind of a package, like a bit like TensorFlow and PyTorch, or it has a couple of like packages developed, and one of the biggest ones is Penny Lane, and I'm kind of involved in developing it. And maybe I'll just go through it very quickly, but for those of you who like to see code, this is how you would describe this quantum circuit that I just have, where you just have the qubits, you don't do anything. In Penny Lane, you would kind of define a device. This device is, in this case, just a simulator that runs locally, but it could be hardware in the cloud or whatever. And now you define your circuit, and you see nothing happens, and you return the probabilities. And if you run the circuit here, so this is very Pythonic here, as you can see. So you get kind of the probability distribution out. You see it's 1, 0, 0, 0, which means your state was in 0, 0. And then you can actually hack the circuit and call for the internal state. That's this complex numbered state. And you see it's exactly what I wrote down. So you could try this at home, basically. If you go to Penny Lane AI, you know how it would. Let me just check. Cool. So I just want to get you used to this picture here. So now in quantum computing, what we do, we always describe time evolution, or what we do with qubits with these wires here. So we just draw these lines, and then we have these boxes that describe the gates. So this is basically a circuit diagram like in electronics. And a quantum circuit is always this big, you can describe by this big unitary that does something. And as we said before, what does anything that I do to a quantum system, how can I describe it? It's a matrix that's multiplied by this vector, or the vector is multiplied by the matrix. So any quantum algorithm can be written as a unitary matrix multiplied to this initial state. So that captures all of quantum computing. I think literally all of quantum computing. There's a couple of games you can play with, like post-selection measurements and stuff like that. But this is always what it is. And then you get like some other states. So you kind of turn your vector on the blosphere. In kind of programming languages, you could define a unitary matrix, and there's actually like this kind of like hacky operation where you can just say, apply this qubit unitary. And now you can run your quantum computer in 2 modes, and this is quite essential. You can, in machine learning, you would always call it a generative mode and a deterministic mode, or discriminative, I don't know. Essentially, a quantum computer will always give you measurement results. So in the easiest case, it will give you these samples, these bit string samples, to tell you what the states of these qubits were after you applied this unitary. I'll just jump over those. But I told you that quantum, or like, it's sometimes very hard to describe computations with like a stochastic outcome. So another way to define actually the outcome of a quantum computation is you measure and then you average. And this is this expectation values that I was talking about that play a very big role in quantum theory. So now if you've got, so if I go up again, if you've got the state here, how would you now describe the expectation value? And as before, you see this is again this quadratic form. You kind of like have the state here, then you have it from the other side complex conjugated, and you sandwich basically your measurement operator that describes what measurement are you actually performing with it. So as a summary, the outcome of quantum computations, at least when you take a deterministic outcome like an expectation value, can always be described as this like quadratic form that is done by like applying like a unitary matrix to an initial state. And then the last thing to say is kind of like that, obviously quantum circuits consist, so you don't really like define a quantum algorithm by saying this is this big unitary matrix. I mean, this matrix is so big, it lives in probability space, right? Like you can't really describe it. So what you actually do physically, you apply local operations. You just rotate 1 qubit, or you apply something to 2 qubits or something like that. So you actually have this chain of matrices that you apply. And why I'm saying this is not just like, I'm making this up, but most quantum simulators, like the simulators that actually simulate what a quantum computer does, they actually literally implement this type of linear algebra, which is why you can't really scale it, because they need to multiply 2 to the n by 2 to the n dimensional matrices with each other. Okay, I'll just skip over that. A little hint that you won't find in the textbooks very much, but what the following is based on is that some of these gates you can parameterize. So they very naturally depend on parameters, because in the lab you would, for example, rotate a qubit, for example, by shining light on it or something. So you've got a field, so you've got a field strength. So in the lab you've got physical parameters that you could actually tune to change the quantum algorithm. And this should be the hint, like this is already looks very much like a neural network, right? You've got kind of like these modular operations that you can like learn and train. So I'm jumping over a few things here. And the second hint that something goes on that's very similar to machine learning is this one here. I haven't talked so far about how to actually encode an input into a quantum computer, because this is just part of your algorithm really. But if you want to do it explicitly, you can say you apply actually a circuit at the beginning that depends on X on your input somehow. So the circuit changes with whatever X this is. Could be anything. There are lots of standard way of how to like define these input circuits. But what's going on here in our really high dimensional space, in our linear algebra operation basically, is that that you apply a matrix that depends on X. So what you get out of it is a vector that depends on X. And for those of you who work a lot with kernel methods, like a high dimensional vector that depends on your inputs is a feature vector. And it's actually quite interesting that you know, these vectors in quantum theory live in Hilbert spaces. And you know, kernel theory talks all the time about reproducing kernel Hilbert spaces. So all the properties that we're interested in kernel theory, we almost get automatically out of quantum theory. So that's kind of the two hints. Let me do the following. So just to kind of like finish this off, or kind of make a bridge now to this idea of how to use this quantum computer now as a model, as a neural network, for example. I want to go back to this like kind of code example here. On the left, you see just a torch, a standard super stupid didactic like torch machine learning example where your model is defined here, and then you've got a loss, average loss, and you optimize here at the bottom. And this is the same example written in the quantum machine learning framework, which actually integrates to Torch or PyTorch, so you can use your machine learning library, and then you just plug in the quantum part here at the yellow thing. And the thing you see is that the only line that's different really, except from like importing Penny Lane in this case, is really that the model is now replaced by a quantum circuit, and the quantum circuit kind of has this embedding function where it takes features X, and then it has like layers or something where it takes weights. And so the structure of a quantum algorithm is kind of like very similar in some sense to, you know, like a machine learning model. And this is running code. So you could just run this and train the quantum model like you train another model. So that's the big idea. I'll do another like 5 or 6 minutes into that section. And then I think I'll pause for questions and continue tomorrow. But I think you've got the basic ingredients now to already understand what I want to say. So I just deepen this a little bit. The first one, maybe we actually finish that one. If you use this example here, and if you have this framework, so for those of you who code, like, you know that PyTorch, what it basically does, it thinks a lot about gradients of functions. So it's a framework for automatic differentiation in some sense. So what happens if PyTorch this little piece of code, the first thing it asks is for the gradient. And there's a big, can you actually get the gradient out of quantum computation? This is not trivial, because you can't just do backpropagation in some sense, because A, you can't really like hack into a quantum computation. If you get intermediate results out of it, it will, how do you say, it will destroy the system. The second thing is, maybe even if we can get errors out of it, maybe the computation itself to get a gradient, you can do it on paper, but it's not a quantum computation. So what means like you can't get it out of a quantum computer, so you're stuck. And there's a very beautiful result, so that we say like, how can we optimize quantum circuits in gradient-based optimizers? And that result, and I will only sketch it very like high level, goes as follows. If you now have this like big pipeline, you know, your torch cost function or TensorFlow or whatever, I'm only talking about these two frameworks, obviously, like take your favorite one. And now we've got these quantum nodes, these little quantum computations in there. And the quantum node basically sends parameters to the model, maybe inputs and parameters, and then gets out like this expectation value here. How can you get the gradient of the quantum node with respect to like, or the partial derivative with respect to parameters that are fed into my gates here? And the answer is, and this was like kind of first kind of found in this paper, and oh, hang on, the last one disappeared here actually, yeah. So this one was just from a couple of days ago that even goes to higher order derivatives. But the answer to this is that in many cases, you can just run your quantum computation twice. You take the difference of the two, and that is your analytic gradient. And what happens in each run, you actually shift the parameter with respect to which you want to take the derivative of by an amount to the right and the left. Now, if you've done, you know, thought a lot about gradients, you'll immediately think, okay, this is just numeric differentiation, right? I wiggle a bit to the left, I wiggle a bit to the right. But what you get out of numeric differentiation is an approximate gradient that is as good as like small you can get this parameter. And this is actually something we can't really do on noisy devices because our outcomes are much too noisy for this. It turns out the geometry of your quantum Hilbert space allows you to choose this as a very large parameter. So it's a macroscopic shift. Just to wrap this up, so these are called parameter shift rules by now, and there are lots of them, and basically getting gradients out of quantum computers is a very big research field that's quite interesting. There are a couple of like cool results of how to make a quantum natural gradient optimizer, or how to use double stochastic gradient descent, because you have something called shock noise when you measure, but you also have the noise from like, you know, taking batches of your data sets. So there's a lot of cool games you can play.
Maria.
And
Maria, we got one more question from YouTube stream.
Cool, thanks, yeah.
Why do you prefer Pennytail rather than Cirq and TensorFlow Quantum?
Yes, so Cirq is not a quantum machine learning framework as such. So Cirq, Qiskit, and all of those are frameworks like that are for quantum computing in general. So PennyLane is specialized on quantum machine learning. There's no reason why I prefer PennyLane except from that, you know, I'm developing it, so this is the language that I'm very native in. So there's TensorFlow Quantum came out a couple of months ago, which is a plugin into TensorFlow, which has a bit of a different, like, you know, like every programming language has a bit of a different focus. So PennyLane is more like hardware agnostic. It doesn't matter what the backend is or what the simulator is. It can use TensorFlow or Torch or whatever. TensorFlow Quantum is optimized for TensorFlow. So if you're a TensorFlow programmer, I would definitely like check that out first and see what happens. Yeah, and I think it's also nice because this whole realm is really growing. So there's more and more interest in those quantum machine learning specialized frameworks. So I think except from TensorFlow Quantum and PennyLane, there's also an academic library called Tequila. So there are a couple of frameworks. Yeah. So no repreference.
Thank you. Thank you.
But I just closed this, I think. So I don't want to talk too much either. I closed this with also this like, so now, you know, this is all very like engineering, like how can we get this to run? How can we, so there's a lot of science behind it, but a lot of it is also just like try and error and seeing which optimizers work and whatever. But there's actually a lot of like interesting questions. So now is where like having things quantum actually changes a couple of things. So again, the geometry of this Hilbert space that I was talking to earlier, that probably gives you these parameter shift rules, also gives you a problem. And the problem is in the community called barren plateaus. So this comes from random matrix theory and something called concentration of measure, that you can show that if your Bloch sphere grows, which means you just have more and more qubits, you can show that your gradients vanish. So basically, if you take a circuit, special types of circuit that it's proven for, but people say like it's true for like lots of circuits, and you randomly sample parameters, so starting point of your optimization algorithm, you have a very, very high chance that all your gradients are zero. And this is like something that gives us a big headache at the moment, but they are very interesting, you know, as in deep learning. This was also probably deep learning at the beginning, and there's lots of really cool stuff coming up now, how to avoid this. And then tomorrow I want to continue basically, I think I'll actually finish the material all tomorrow, but I'll continue on this, like using quantum computations as models. And I want to talk about what are these models actually. I gave you already hints that you can compare them to neural networks and to support vector machines if you want. So this is what I talk about. But also as a bit of a background information, now in this near-term quantum machine learning community, lots of people, so we suffer from the same syndromes that machine learning is suffering from. We put papers out where we kind of just put benchmark tables and say this is working well. And now here's the crux, like it's working well on an iris data set, or compared to a neural network with a single hidden layer and 2 neurons or something like that. And I especially got a bit upset in recent years about this because I thought, like, we're physicists, we should actually be able to analyze the mechanics of these models. We should be very critical about them. And this question, what do these models actually do? What does quantum give you? It's not a magic ingredient. Maybe it's just something extremely stupid that the quantum computer does. That's kind of coming up in recent years, and I think this is very, very, very interesting to follow. Great. Okay, cool. So I'm kind of like finishing. Maybe if there are any other questions or.
Yes, we got one.
Yes.
During training, if we have a lot of whites, Do we need to shift every white to the right and to the left independently in a circle? Or is there some trick?
Yes, if I understand the question correctly, it's actually a very, very sharp one. That is that basically, you know, in backpropagation, you have tricks. You don't need to like run your circuit, your model. You know, if you've got n parameters, you don't have to run it n times because you can kind of share errors, and there's like very clever ways. In quantum computing, that's unfortunately true. So as far as we know, you have for every parameter in your circuit, you have to do this shift right and left. At least for standard like settings. And so in some sense, we cannot use like really, we can integrate quantum computers into automatic differentiation pipelines, but we cannot really differentiate through them with these very, very effective methods. So yeah, quantum computing will always be linear. So computing a gradient will always be linear in the number of parameters. And that's kind of in some sense like maybe a bit of a problem, but you know, anything is possible. By the way, why is that so? This is actually very fundamental based on no cloning theorem. So in quantum computing or quantum information cannot be cloned. You cannot just prepare a state and then say there's an operation that just clones the state to another one, and then I've got two of those. So this is like one of the problems.
Thank you for your answer.
Cool. Also, if you want to talk to the organizers, if there's something, you know, after hearing this and you're still keen to like listen to tomorrow as well, if you've got specific questions for tomorrow that I should just talk about or illuminate again or something like that, then I can prepare better for what you need. And yeah, so feel free to kind of get them to me somehow through the channel.
Maria, we got one more question, if you're not against.
No, not at all. I've got time.
We have about 4 minutes left, so I think we have time. What is the essential difference between classical quantum computing and near-term quantum computing? Does near-term quantum computing also rely on superposition of states?
Yes. Oh, sorry. I wanted to mention that because obviously you were waiting for the three words of superposition, entanglement, and interference. And I haven't actually given you where they are. Yes. So all quantum computations we do use superposition, entanglement, and interference. Let me just give you an idea. Wait, where can I actually describe this? Maybe at the beginning section. Superposition just means, well, the opposite of superposition is a distribution like this one, where you just have a 1 and zeros else. So you have a deterministic result. So you know exactly where what your state will be, your measurement outcome. Any quantum system you can describe by a vector that has non-zero entries here, this kind of like mixed up, is a quantum system in superposition. Why? Because in classical probability theory, this corresponds to uncertainty because you don't know what your state your system is in. In quantum physics, you have to be a bit more careful. We don't call this like uncertainty because it's not only our lack of knowledge, there's something else going on there. And what's going on there is, for example, interference. That's the second term. And this term, talks about the fact that if I multiply a matrix to a vector here that has complex numbers, that can be also negative, then these negative numbers can cancel each other out. So this is very much like in wave mechanics, how you have like, like interference effects there. So yes, superposition, interference, and entanglement is nothing else than if you have a circuit, I'll just sort to here. The moment you have like interactions or actions that happen on two qubits at the same time, they can entangle those qubits. So in short, if I like write a circuit here, it depends a bit on how the circuit is built. So I could also construct examples of circuits that don't entangle, that don't use superposition or interference. But usually and very, very easily, all of those circuits will create a state that has all those properties. So the state in the end is really a quantum state, and this probability distribution is really a quantum probability distribution. Thanks for the question. Actually, I forget to mention that.
Okay, thank you, Maria, for your answering. So we have only 1 minute left. and the participants also writing to you. Thank you.
Okay, thanks.
So I
Maybe
hope
stop
we'll
this.
meet tomorrow without internet breaking or something.
Perfect. I do my best. You never know here in South Africa, but yeah.
So thank you for the lecture. It was brilliant. See you
Thanks so
tomorrow.
much. Bye-bye.
Bye.
Thanks, guys.